to the present, as they say. Well, here's one we saw earlier, but with different, essentially just different numbers. So,
is this, do you know if this is a morning or an afternoon exam, this one?
Morning.
I mean, you're probably the wrong person to ask, but...
I'll be there, so I've
heard it's a morning exams, okay, I've heard it's a morning.
I'll need to know.
Yeah, 9 till 12, I think.
Please, folks. Right, so 2012. First question is basically one we saw earlier, but we've changed the PU to U, so numerical values different and so on. The same needs to understand efficient. Doesn't like the spelling efficient. I don't know why it doesn't like that. But, okay, so again, we've done that. I don't think there's much we can say. It's embarrassing seeing all the papers fly past with so many years all in one morning. I don't normally do it quite like this, but inevitably there is a degree of repetition. There's only so many things we can ask, there's only so many equations we derive, so here again, just derive. Well, this is the neutron source problem again.
It's not the exact same question, though.
Inevitably it's close, but in a way that's what we want. At the end of a course like this is the sort of thing you need to be able to do, so I don't see any problem with that. Other than giving you numerical ones where the numbers are different, which feels, in the end, a bit pretty trivial. You know, it's a bit almost insulting to say, well, it's different because the numbers are different. Okay, so resonant escape probability, fast fission factor, we've talked about that. And oh, that's okay. This was an opportunity to get something a bit different. I weighted it relatively lightly, I guess, but I wish with hindsight I would have done it more. So what would be different if we went to a two-group analysis? What do we mean by two groups as opposed to one? What are we talking about?
Two energy groups?
Yeah. So if we think about what goes into the various terms in the various physical processes, never mind terms in the equation. In our one group analyses, we've got, which is everything we're doing, the production of neutrons from fission and their absorption and so on. And that one group is rather bravely encompassing everything from fission energies down to thermal, so a factor of, what, 10 to the 8 in energy. And if we were only slightly less brave and had two groups to cover a factor of 10 to the 8, 10 to the 4 each, let's say, what different terms would crop up?
Scattering to lower energy.
Yes, and is that a source term or a...
That would be a loss term in group 1.
Yep.
And that would be a source term in group 2.
Absolutely spot on. So our upper energy group, its source term would be fission, just like our one and only group has fission at the moment. And it probably would have some absorption, not a great deal, but there'd be some. But its big loss mechanism would be loss by neutrons scattering down to energies that meant they were no longer as part of that group, but they've joined the other group. So there's a kind of an extra dimension via which things can escape, as well as they can escape in energy space as well. So that would be the main change. So there wouldn't be a fission term in the lower energy group. There will be a downscattering term, it would be known as. Of course, this is how this would be analysed in the real world, but with multi-groups, 10 more groups, just depends on how big your computer is. And then indeed you might actually have some upscattering terms, because neutrons could have their energy raised in some collisions. Certainly from thermal groups they could go up, so you might have a bit of upscatter. But you can see obviously it gets a little bit more complex, and I think, how the hell do you ever measure cross sections for that? What is the rates at which these upscatters and downscatters happen? It's a hairy business.
So they're all born at the one energy level and then they just drop into various groups. If you look at a multi-group situation.
Yeah, they'd work their way down through them. They're all pretty much born at the 2 MeV fission energies. No doubt there's a range of those, but I don't know if that's ever taken into account. But as they scatter down, yes. So you have a balance for each group rather than a balance for the entirety. So in our conservation statement for the neutrons, as well as being lost spatially or being absorbed, they can be lost out of the energy space. You know, they cease to be within that energy band. Yeah. So that would be the main change there that we'd be looking at. So we'd have needed to put in, clearly the terms, which are then going to be, we would refer back to and say you do or you don't have this, and so on and so on. Okay. So, cylindrical reactor criticality problem, evidently. We've got the composition data for the mixture down here and the various other things we need to know, resonance, escape probabilities and so on. And derive the critical, oh okay, so it says 15% there, derive the criticality condition for a cylindrical reactor. Well, you know what the result is, it's in your data sheet, so you've got to go through the process of demonstrating it. And when you do something like that, do more than just rattle down the equations, put in the odd words so it's clear that you aren't just reproducing algebra, and you've got some, you do have some inkling of what it's all about. Because, you don't, particularly since the result is presented to you, either in the paper itself or in your data sheet, plainly putting in some very sketchy algebra that ends up in that result is not necessarily enormously convincing to the reader. So if you put in enough words to make it clear you know what the equations you're writing down are actually telling us, that's important. Now, we don't write an essay, but just put in enough to make that clear. Okay, well that's asking you there to draw the little sketch that we've drawn a few times and showing how we can now choose combinations of R and H for our drum, and give numerically any asymptotic values, so it asks you to work out those two values there. What's the radius at which even an infinite height doesn't make it critical? What's the height at which even an infinite radius doesn't? You're not looking aggrieved again, are you? No? You make me worried, you see. What have I done? I think unfair or something. I don't think it is. Yeah. Right. Okay, and it says choose a particular height. So what's the diameter? So you're just picking off something off that graph, but doing that numerically. And what difference would it make if the steel from which the drum is fabricated was itself heavily borated? And would that make any difference? Would it matter to you? Why would it matter? Fair enough. Okay, you have to choose one. In the analysis you had done for the cylindrical criticality, you have assumed the flux is zero at the boundary. It's a bare sphere surrounded by an infinite vacuum universe. That's another way that any neutron that got to the boundary was lost. Well, it can be no more lost by being stuck in boron than if it shot off to outer space. So your analysis has already been the analysis appropriate either for a drum in an infinite vacuum universe, or equivalently, and physically it must be the same thing, a drum made of heavily borated steel. They're the same thing. So again, what it's actually asking is to make sure that you really understood what was the physical basis of the bit of analysis that you were just doing, and not just indeed reproducing the algebra, which is where I started. So would it make any difference if it was borated? Fine. Oh, and then here's a criticality one effectively again. We're now going to store these drums immersed in water, well separated from each other. What effect might it have? What, if any, difference would it make if this cooling water were to be heavily borated? And that's, you need to have known what you're talking about to get all of these bits right, don't you? If you got the borated steel drum right, you'll probably get the rest okay. Unborated water, unborated drum, we've got a reflector, but heavily borated water, we're back to the infinite vacuum surroundings. So again, it's easy if you, well, it's like a cliche, isn't it? It's easy if you know, or it's easy if you followed what we're doing. You'll get it wrong if you haven't.
You know, it's like, if you've got an underwater drum in water, even though the water is a reflector, because the flux at the boundary of the drum is zero, it's not, it's reflecting nothing, surely. Because
We assume that the flux and boundary is zero.
so your assumption that it's zero, then it doesn't matter that there's a reflector there, because it's not reflecting anything.
Yeah, I could argue, we're sort of going to argue about how many angels can dance on the head of a pin at this point. Because I'm not disagreeing with you. Flux is that shape, zero at the edges. You're telling me at the edge there's no flux, true. At the edge there's a big flux gradient, so there's a big current. How can you have a current when there's no flux? And absolutely, that's right. It's the, you know, the logical infelicity we end up with as a result of that assumption we've made. It's not a bad approximation we've made, actually. It's not bad at all.
Could you argue logically both sides of the argument then for that question?
No, all you'd have to say is it's a consequence of the approximate analysis we've done, and we have to interpret the results of our analysis bearing in mind the approximations we put in to make it and interpreting them sensibly. So, you know, we're not mechanistically and blindly doing what the algebra tells us here. We're saying, how can we understand what's going on physically? Algebra will help us, but we still need to think a bit about what's going on. And okay, we've artificially forced the flux absolutely to zero. There are minor tweaks to the method where we don't force it quite to zero, and that overcomes that problem. But you know, as long as we don't ask a question which we know our model has, to which we know the model has precluded a sensible answer, because that is the case. If we've forced the flux to zero, how can you have leakage? That must be true, obviously. But if we understand enough about what we've done to see why that's obviously going to be a consequence of the model we've chosen to adopt, but we know it's going to be one of the wrong things it'll tell us, but because we chose the model we know about it, we're not going to interpret it in that way. That's right. So it's a slightly more, what do I say?
Real world approximation. Also.
Yes, or it's a more sort of robust, it's almost a more mature way to think about the algebraic analysis you're doing as an engineer. It's not blindly saying the algebra is right. I made the model up, and this is the results of the model, and if I know some bits of it, it tells me are plainly rubbish. Well, that's probably a consequence of the rubbish I put in, as long as I know what it was, and I know, therefore, for what purpose, what inferences I should draw from the predictions of my model and what inferences I should not draw, and that's fine, and that's exactly what we're saying.
Using the assumptions based on the situation. So, for example, like you've now got this water surrounding the drum, you kind of change your assumptions a little bit.
Oh, absolutely.
So
then
you're
we'd.
saying the other flux may not be zero.
Yeah,
for this
then
particular-
yeah, very much so. Because the difference is we'll get a significant number reflected back, and that brings the edge of the flux. The flux won't be zero for the bare drum, and there is an analysis that would cause it not to be zero.
But it's too complicated.
It doesn't add a lot. No, it really doesn't add a great deal of complexity, but it doesn't add a lot of insight either.
So if the Bohr-rated situation represents the point kinetics approach, does the unbohr-rated situation
No, I'm confused.
so the assumption of point kinetics would be the same as you having a Bohr-rate surrounding.
No. I think you're risking. The point kinetics is what we've really got is a flux that varies with at least 2 spatial coordinates and time in general. And what we discovered was that well, we set the time to zero in an eigenvalue approach at time dependence. We discovered that it was separable in space. It actually turns out it's pretty well separable in space and time. So we can think of the time dependence as captured in just a pre-multiplier to everything, giving a time dependence, multiplying phi r of r times phi z of z.
Yeah.
So it's actually separable in all 3 dimensions.
Yeah.
And the point kinetics approach effectively says, well fine, we'll forget the spatial variations and just solve for the temporal.
Yeah.
But that's no different in kind from what I did when I said, well, let's forget the spatial variations by pretending it's infinitely big. It just seemed a slightly simpler way to get to the same thing.
Yeah.
But
What I mean is the assumption in the point kinetics approach is that you have this infinite surrounding.
no, what it says is whatever is the spatial variation, the temporal is a pure multiplier on it.
Okay.
It's separable. So it doesn't say of itself anything about what the spatial variation is. It just says whatever it is, it's going to stay broadly the same shape and move up and down bodily in time.
And the reason the answer to
But there's nothing on this about point kinetics or time, I think, which is why I'm slightly intrigued as to why you're asking me.
Okay.
I mean, you're welcome to ask, so I just couldn't quite think what prompted that question.
Yeah, well, the reason I'm asking is because so when you said would it make a difference if you had it wouldn't make a difference if the cooling water would be heavily borated, and the answer is no.
Well, we've got to be careful. In some cases, think carefully. A bare cylinder, we have a certain criticality condition. If that bare cylinder is surrounded by borated steel, it won't make any difference because that's implicit in the treatment of bareness.
Oh, sorry, I think I wanted to say bare instead of point kinetics earlier.
I was one. Okay.
Yeah.
Yes. Well, let me talk this through from the beginning.
Okay.
So the bare cylinder, we've got the ordinary criticality condition. Heavily borated steel drum, it's the same as bare because nothing's coming back. Bare cylinder immersed in water, we've got a reflector, so it will now be supercritical if it was just critical. Bare cylinder immersed in heavily borated water, we're back to being bare, it doesn't make any difference.
That's my mistake. I wanted to say bare rather
Okay.
than
You can see why I was puzzled.
my mistake.
Right, was there other questions on this one or shall I move on? Right. Well, that's question 4, by the look, because that's the end of that particular year. So working, if this is useful, I'll happily carry on. I'll just find number 13. Oh, something's gone wrong with the formatting, but there you go. So explain what is meant by each term in the expression k infinity equals. Well, again, I think we've been there in various guises, so I hope that's fairly straightforward. Making clear distinctions with regard to neutron energy. Yes, to express that clearly and correctly and completely, you've got to be quite careful in the phrasing and make it clear you understand what you want. Where parts of that analysis are addressing thermal and therefore what we have to do in order to make it describe a system in which things are anything but all thermal. So that's one. So using the point kinetics approximation, or equivalently throwing that away, it becomes the same thing. Get the time-dependent power following a step insertion with no delay neutrons. Oh, well, okay, that's very much the same as we had before, that's fine. Although that time we didn't give you the result, so plainly I was feeling a little bit more aggressive that year.
That's since 2009, the first one we did with the power energy.
Well, the difference is you didn't get given the result there, so you had to do it even more blind, as it were. Yeah.
So just so you know, for part A, then I mean, if we really said what each term means, then what it accounts for, that would be enough, right? I mean, just because it's easy to like lose marks on tiny things. Nice. If we said like one for the fast fissions, the other for the escape, and music, I forget about that.
Well, I can't answer yes or no.
Sure,
to
of
that.
course,
I mean,
yeah. But
don't just tell me what the symbol stands for. This is the fast fission factor.
Oh, of course, yeah. What do you account for?
The whole thing overall is to say we want to do all our sums based on thermal cross sections, because it's thermal neutrons that are doing this for us. But we're actually making fast neutrons. That's definitely. Sorry, that's someone trying to Skype me from China. Must be picking up some wireless from somewhere or something.
Okay, that's
So derive the criticality condition for a cuboid, and I think strictly, I think strictly parallel pipette is either a special case or too general a case. Cuboid is a better term, but it's never caused confusion yet. That's right, parallel pipette I think could be a brick that's got squashed, so strictly that's not right, but anyway. So, criticality condition and flux shape, well that's straightforward bookwork. I hope you can do that. And find the minimum critical volume. Well, the starting point, and you don't need to prove it plainly, is well the critical volume will be minimum firstly when all three sides are the same length. So it's a cube as opposed to a cuboid. I think we can take that physical common sense. And therefore, for those, if that's the end of the question, that seems rather a gift. So we've given you sigma A and K infinity. So from that you can work out D upon sigma A. You've got L squared as well. Everything is there for you. So there's no little table even to work out. So what is the actual volume in cubic meters? It may go on over the page. I can't remember. No, so that was, well, it was a short question. It was only 15, so it was less than pro rata, as it were. Again, that was slightly different, but makes a change. So, a more sort of quote realistic question. Here are the dimensions. Because in practice, the dimensions are as like as not going to be determined by other disciplines, not the reactor physics. Thermohydraulics, probably more than anything else. How big a core to get the heat out and so on. So you're given the height and diameter, and you're asked to find out how much 235 is needed, and I gave you the clue that it's between 5 and 6, because otherwise you can go scrabbling around forever. You could either do it algebraically, obviously just rearrange the equations to solve it once and for all, just pull out the number density of 235 out of the criticality equation, which surprised me. I thought people would find it easier to do it by sketching a few points on a graph. Most of the class ended up doing it, I think, just rearranging the algebra and solving once and for all. But matter of taste, some did both. Either is fine, obviously. But then we said, okay, we want burn up to be 30% of the beginning of life 235. So 30% of what was there to begin with is the concentration of 235 you've just computed. No, 70% in time. That's right. 30% is burnt up, sorry. So we've got to put in more 235 at the beginning. So even after we've burned 30% of it, i.e. 70% of it is left, we've burnt it up down to the concentration that you've just computed. And then says, and if you're going to do that, plainly at the beginning of life you're going to be far too reactive, so you better put in some boron to compensate. So how much would you put, boron would you put in at the beginning, which then you gradually take out as you burnt up the fuel. So it's a slightly more realistic one, and you could imagine expanding that to say, well, when you heat it up we're going to lose so much reactivity, how much extra fuel do you need to put in order to compensate for that, for example. They're the sorts of things.
Could we see the steps in the answers to that question? If you have.
Yeah, I've got the solution. I chose to do it by sketching, I mean, it's straight lines and somehow
Yeah.
you can do it either by that or by 2 points would have done it. Yeah, I mean, I had a spreadsheet, so it's easy just to I actually honed in and iterated and then plotted the graph later on. It's quick on a spreadsheet.
Take 1 and 6 and 1 and 5.
Yeah. So. Okay, so a slightly more sort of realistic question. And then, so the burn-up one, we said we need 70% of the beginning of life, U235, to be the 5.31 we just computed. So if 70% of it is that, can you zoom in just a little bit? Zoom, yeah, sure. So we need 0.7 times the beginning of life, 235, to be the 5.31. So 5.31 over 0.7, we come to that number there. And we need enough 10 boron to counteract that. So we go back to where we were, put in the higher 235 and find the 10 boron to go back to where we were. Achieve that there. And again, there's various ways you can choose to do these numerical ones, but I'll have done something that was easiest because I was using a spreadsheet, but I appreciate you not. I think that was at the end of the question. So this was trying out different numbers, and again, whoops, I did it because it was easy by supplement C. You can rearrange it and just do it algebraically, fairly straightforward. Just much what you prefer. Right, and I think that's the last one on that paper. So the numbering's it. Okay, that's 2013. So the last one is 40. This is the one that was put up yesterday. I think it was on the website before, and I received the complaint. I don't know, not it, that it hadn't got numerical answers on, so I caused it to be put up again yesterday, or replaced with one that had got numerical answers.
Oh, so we have got the numerical answer on this sheet.
Sorry?
So you've given us the answer to get to.
Yeah, if this is the one with answers, it's the one I've just should be the same, except for the fact, well, it loses a little bit of formatting probably because it's a PDF. It's going to be harder to look at. Bear with me.
Did we not skip a question in 2013?
Did you what? Sorry.
Did we not skip a question?
Did we miss 2013 out?
Like the last question.
Oh, a question.
I
Oh,
think.
not intentionally, but I'll go back if we did. Bear with me. But I'll put this one up now. So.
Unless you intend to.
I didn't intend to. Right. So just to firstly to find the numbers, yes, I went in and added some numbers in the only numerical one, so that's the only change you've seen there. Okay, so first part there, just an absolutely straightforward derive, from the notes. But again, when you do these derivations, it's not enough to regurgitate the algebra as fast as you can. Put in at least the odd word or the sentence to give some confidence that you know what you're doing. Otherwise, it's we can't just give full marks just for the algebra. So those set of 6 or 7 equations. And discuss how it behaves for drops and rises, so step inputs of reactivity. And the only way you can see the response to those is by solving the equations.
It's a few times the delayed neutron factor.
Yes.
There's only one result of reactor blows up.
Yeah. And a few times it's on the step down is slightly different.
Yeah, well, it shuts down.
Yeah. But again, not
Yeah.
bang. So things like prompt jump and prompt drop are worth reading about to see which of those become relevant under which of those circumstances. Yeah. And anyone who's used the tools we have which solve those equations, because just looking at those equations, without the delayed neutrons you could look at the equations and get a lot from the behaviour. Obviously it's simple. Looking at a set of 7 coupled equations, you can't get a great deal from it without solving them. Plainly solving them is tricky, which is why I've given you something that will solve them and allow you to put the numbers in and see how it behaves. That's what it's for. So I know some have done that, but I would encourage more generally that you gain from doing that. Otherwise, okay, you derive the equations, they're not telling you very much at that point. Okay, so we've got the bare cuboid derivation again. Fluke, they were adjacent years. If it's of any interest to anyone, I absolutely don't look at the previous year's papers to think, what did I ask then? I'll make sure I ask something different this year. So it's as likely to be like last year's as similar to 5 years ago, because I really don't try and play the game. I just do it blind. I can guarantee I will have forgotten, so I know it's a random choice then. It really isn't influenced by what was there before. So, okay, that's slightly more awkward on there, yes. So compute the side if it's a cube, and then if it's surrounded by an infinite reflector, how much would the volume go down? Well, again, you need to know what the reduction in dimension was likely to be.
Yep. With the C question, deriving the criticality condition for reflected two-body is rather a lengthy operation. Would it suffice to simply...
Let me stop you there, as they say. I couldn't derive it full stop. I don't know if it probably could be derived. I've never seen it derived, and I wouldn't wish to derive it, and I wouldn't inflict the derivation on anyone, let alone even you.
Would it simply suffice to say the reflector removes a diffusion length of critical dimension,
like we did for the cylinder in the previous year.
Therefore, the composition of a reflected critical cuboid is equivalent to the composition of an unreflected critical cuboid which has the critical dimension of A plus the diffusion length.
Got lost at the end there.
In the exam, I will draw a sketch. You have 2 reactors.
All we're saying is, it was this big, I've made it 10 centimetres smaller all round, how big is it now? Honest, stop there. That's all we're saying. Nothing more complicated.
How big it is? How big it is?
Well, it asks for the fissile content. So if that's the composition, and we can make it smaller.
Okay.
So
No, I assume that the question is, how do we have to tweak the composition to get it critical at the same shape despite the same size despite being reflected? That's what the question.
I take your point. You could. I would. If people had answered either of those, I would have marked them both and both would give them full credit. Yes, that's an interesting interpretation. I can't think now which I actually meant. I know everyone did what I meant all the time, because I remember not, I don't remember being surprised. But then you weren't in the class that year. I'm looking forward to this year's paper. What an unbelievably bizarre interpretations can be made. I look forward to it.
So in this case, you were not you were only looking at the volume. You were not looking at calculating the concentration of U-25.
Looking at that, just reading it more carefully now, what fraction could the content be reduced?
So how do you get that number? What equation calculation gave you the 8%?
Yeah, no, it must be, because I don't think, given what we know, I don't think we know enough to compute what percentage reduction would do. So you're quite right, you're safe there.
Have you got the worked answer for that part, so we can see what you actually did do, just to clear up confusion?
Well, I'll look see if I've got that. Just trying to find the. Yeah, we just worked out the reduced volume, which is all you can do, look at it more carefully. We just worked out for that new dimension what is the new volume, and that gives us the reduction in fissile material. Right, what are we on? 2040. Yeah. So 2014 paper. Oh, here's the xenon one. Yeah. So describe what's going on in words. Write down some equations for each of the two species we need to know about for the xenon. That's the iodine and the xenon. Hello. Yes, I'm going to. Sorry, we've been waiting there all this time. I do apologize. Quick, come in, so at least you can see it. Who would like to move in a couple of minutes into tutorial mode to get direct numerical help on questions? Quick show of hands to make these folks feel needed. Yeah. I think
I was hoping for it,
they've shown their value. What were we were needing something done on the website that someone's going to remind me about, but now we have people here who can do things like that. Who was going to email me?
Solutions for the film hydraulics example sheet would be good.
No.
Well, that's one. Well, I don't know.
No one has anyone got those?
I can't find them
No,
anywhere.
right.
He gave them by printing.
No, he tells me that Ronac had them electronically.
I have access to your web blogs.
Well, we first of all have to have the.
I think you have
The solutions.
Jeff forwarded them to me.
Okay, could you put them onto Blackboard? And maybe just for good measure, if you stuck them onto Moodle as well, just in case it's hard to say the reactor physics bit for Moodle, just in a separate folder.
Okay.
But do that as well. I mean, just because in case some people find one easier than the other. Sorry. My watch thinks it's 5:13. Oh, that's sad, isn't it? I don't know why it's wrong, but that's my alarm. That's a strange time. If you could do that, that'd be great. Thanks. So that's Jeff's thermohydraulics solutions problem sheets.
For actually,
I set my alarm at 5 o'clock every day. 3:14, 1:05.
Can I leave?
Right. So we've got our equations for the iodine and the xenon. So that's first of all just write the equations down. So we're here trying to lead you through step by step. And this next one, I think this was of a year before I had become slightly more user-friendly. It actually then asked you to solve the equation for the ID number density following startup. Oh no, for the equilibrium, I beg your pardon, ignore me. It doesn't say solve that, it says find just the equilibrium value. So rather than solve the differential equation, you're just looking for when d by dt equals to naught. And since the equation is of the form d by dt on the left-hand side equals some other terms, it's easy, it's just those other terms added together equals naught. That's the steady state. And it's much easier to solve for what the equilibrium value is than the exact form of the transition to the equilibrium.
You actually get a number for that value.
Well, it's algebra equals algebra, and then when you put the numerical values in for cross-sections and fission yields, you can work out. So first of all, it says indeed develop an expression for, and then estimate the time required to attain it. And again, because we're not solving the equation, there are the sort of simple approach we took. Say, well, we know it's going to be something like that with an exponential approach to it. So the way I did it was, say, well, let's take the gradient at time naught, and that's going to be at least an indication of how long it will take to get there, and it'll be a handful of those until we're pretty damn close. So that gives us a reasonably good, like a sort of like a half-life, isn't it, that kind of approach. And again, essentially the same for xenon as iodine. Iodine obviously is the easier one, and it then features in turn in the xenon equation, because if you think of the mechanisms for making the xenon, there's direct production from fission, there's the decay of iodine into it, so those are the two mechanisms forming it. Its own decay is a mechanism for losing it, and it gets burned up by neutron capture. That's another way that it disappears. So there's 2 ins and 2 outs for the iodine, and there are just one in and one out? I think just 1 in and 1 out for the, so that's the wrong way around, 4 for the xenon, 2 in and 2 out for the xenon, and 1 in, 1 out for the iodine, but you've got the picture in your notes. And reactivity reduction due to fission product poisoning. So that allows you to compute the xenon concentration. So that adds to the absorption that's going on in the core. So we know the change in reactivity is essentially the fractional change in absorption. So that allows you to make an estimate of the reactivity reduction due to the xenon. Okay, that's it's really, and all that I think is in your is in the notes, so it's really straightforward. If you know the material, you're okay. And then 4, draw a chart of the life cycle. We've talked about that, and introduce the idea of multiplication factor, and discuss how, whilst it really applies to a one-group model, we can do things that make it actually able to take into account the energy ranges that exist in the real reactor. Okay, that was a question before. Did someone say we'd missed out a year in our...
You just, the last question, 2013.
2013 we missed the last question, did we? Okay. That was 2013. 2013. Oh, 4, okay. Okay, well, this looks fun. Surplus missile material. So we've got an array of well-spaced, very tall vertical cylinders in underground cavern. Calculate the number density if it's half of what would cause criticality.
30%.
Okay. So essentially that's the criticality of a cylinder, but when the cylinder's gone off to infinity. So you could either derive it from the beginning for an infinite cylinder, I guess, which I've never actually done, but it can't. It must be. It'll just be like the regular cylinder case, but simpler. or you can derive it for the cylinder as we have done and take the asymptotic value. And to improve cooling, it's proposed to flood the cavern with water. And how would that be overcome? Fine. We've dealt with that in a different context. And then you've got the numerical values for the...
The way that we overcome this would be to store dry fissile matter instead of in a solution.
Yes, if you could reduce it down and make it into a dry residue.
It would
I guess
also
it depends what it
shrink
is.
dramatically in terms of volume.
Yes, the decay heating rate would increase dramatically in terms of watts per cubic metre as well, and that may be the issue. And also boiling down tons and tons of water containing nasty stuff is not a trivial business. So, but yeah, I'm not disagreeing with you. There's all sorts of nasty choices to be made. Right. That has brought us back to the present day, as it were. My voice is about to give out, I think, after 3 or 4 hours non-stop. So any final questions before, well in this case, as it were, before the show goes on the road? I mean, this course is actually about to go down to Australia end of next week, I think, and start all over again. That's fun. So anyone who missed it first time round, you can come and resit the course.
Pay for a flight.
It'd be a good revision, a good 2-week revision programme for you. You can just resit the whole course in 2 weeks. There you go. That's
Where in Australia?
Sydney.
Oh, okay.
Very well.
Yeah, all right.
Right by the beach. It's nice. Sit looking out at the sea.
Melbourne, but okay.
So,